Hello students, today we are going to see the new lesson which is laws of motion, and this is the session 1, and today we are going to see these topics. See, each and every object in the universe interact with every other object that we know, and in human interaction we not only interact with the nature, but we also try to understand and explain the behavior phenomena of each and everything scientifically. So in laws of motion, the scientists have predicted a lot of laws regarding this motion, and earlier our famous scientist Aristotle said that force causes motion. Actually, this statement is based on the common sense, but any scientific answer cannot be based on the common sense. It has to be proved. It must be endorsed with the quantitative experiments and proof. But after Aristotle, in 15th century, there came another famous scientist, Galileo, and he said force is not required to maintain for motion. Okay, so it is not depend upon the force. Actually, he challenged Aristotle with the idea of by doing a series of experiments. He said force is not required to maintain the motion. He proved with some examples. See, in this picture you can see the initial position of the ball at L1 and the final position of the ball at L2. Okay, the surface is rough and the inclined plane have the same angle. Initial and final positions, the inclined plane will have same angle. Due to that same angle, the ball rolls from the top of an inclined plane to its bottom. After reaching the ground, it moves some distance and continues to move on to another inclined plane of same angle as I shown you in the figure. Let's see what's the second one. In the second one, the initial position is same and the final position is same. That means the angle have not got any change. But by increasing the smoothness of both the inclined planes, okay, here we increasing the smoothness. There you can see some rough surfaces, but here very smooth surface. So by increasing the smoothness of both the inclined planes, the ball reach almost the same height, which is here referred as h, and from where it released. Now L1 in the second and L2 in the second planes. The motion of the ball is then observed by varying the angle of inclination of the second plane, keeping the same smoothness. Here we change the angle of the second plane L2 using some decrease in the angle. Okay, so when you decrease the angle, if the angle of the inclination is reduced, the ball travel longer distances in the second plane to reach the same height. When the angle of inclination is made 0, the ball moves forever in the horizontal direction. See, in the fourth picture you can see all this. Okay, fourth picture, there is no inclination, there is no the final position, so the ball goes to infinity. That means if the angle of inclination is made 0, the ball moves forever in the horizontal direction. If the Aristotelian idea was true, the ball would not move in the second plane. Okay, because as per Aristotle's idea, force causes the motion, but here there is no need of force to move that ball towards that infinite direction. then the ball would have moved into second plane even if the smoothness is made maximum, since no force act on it in the horizontal direction. From this simple experiment, Galileo proved that force is not required to maintain motion. An object can be in motion even without a force acting on it. So Aristotle coupled the motion with force, while Galileo decoupled the motion and Newton's laws of motion. Let's see what's the first law. Every object continues to be in the state of rest or uniform of motion. That means it have a constant velocity unless there is external force acting on it. See, here I gave a picture here. In this picture you can see a boy is throwing a ball to the sun. If there is no external force, okay, the ball will reach the moon. But as per our scientific notifications, and Newton analyzed the views of Galileo and other scientists like Kepler and Copernicus on motion, and he proved much deeper insights in the form of these three laws. He proved that unless there is an external force which is opposing the ball from the sun, it will reach the sun. But there is external force in the sun. That's why the ball reach the ground, because this gravitational force attracts the ball towards that ground. Okay, so here the gravitational force is referred as the external force, and using that we have also find one term, that is inertia. And what do you mean by this inertia? The inability of objects to move on its own or change its state of motion is called inertia. And inertia means resistance to change its state. Even the state can be rest or can be on motion. There are three types of inertia. One is inertia of rest, inertia of motion, and inertia of direction. I know you all well versed in these laws of motion in your earlier classes, probably your 9th, 10th and other lower classes. But here, depending upon the higher secondary, the examples, the terms have been little modified and elaborated. Okay, so study as per your level. Let's move to the types of inertia. What are the types? First one, inertia of rest. The inability of an object to change its state of rest is called inertia of rest. See, what are the examples? When a stationary bus stands to move, the passengers experience a sudden backward push. This is also due to inertia, which we regularly experience this when we are traveling to one or more places. Second one, when you beat a carpet, the dust particles comes out. And third, I gave an example, when it feels it's old, the leaves began to fall down to the ground. It's also an example of inertia of rest. Then second one, inertia of motion. The inability of an object to change its state of uniform speed or constant speed on its own is called inertia. You can see the examples. When a bus is in motion and if the brake is applied suddenly, passengers move forward and hit against the front seat. Okay, that also we can experience regularly while traveling. And the second example is a person trying to get down from the running bus falls forward. And the third example, which I gave in your GIF image, a person take a long run to jump to a long distance. It's also inertia of motion. That long run will give him a force to jump for a long distance than he expected. The next one, inertia of direction. The inability of an object to change its direction of motion on its own is called inertia of direction. When a stone attached to a string is in whirling motion, and if the string is cut suddenly, the stone will continue to move in circular motion but moves tangentially to the circle, which we can see in the centrifugal forces. Then the second example, our protection through umbrella. The raindrops cannot change their direction of motion while they move from the sky. Then inertial frames. If an object experiences no force, it moves with constant velocity or remains at rest. But how do we know whether an object is experiencing a force or not? See, in day-to-day life, we are teaching more and more to the students. But how do we know that they are learning properly? Only way we can do that is through the examinations. Like that, all the objects in the earth experiences Earth's gravitational force. In the ideal case, if an object is in deep space, that means very far away from the other object, then Newton's first law will be certainly valid. Such deep space can be treated as an inertial frame. We can analyze the horizontal motion of the object as there is no horizontal force that acts on it. If there is no horizontal force, then the body is at rest. And we cannot analyze the motion in the vertical direction as the two forces, because there are two forces. One is the gravitational force, another one is the downward direction and normal force in upward direction. See, when you throw a ball to a sky, it will certainly after some seconds or some minutes it will reach the ground. Then the force you used or the velocity you used to throw the ball was zero. So that act on it, the ball, makes the net force zero in the vertical direction. For example, as in the short film I shown here, the car is moving with uniform velocity v with respect to the person standing at rest on the ground. As a car is moving with constant velocity with respect to the ground, to the person is at rest on the ground, both frames, that means the frames with respect to the car and to the ground, are inertial frames. Okay. Now, what do you mean by the non-inertial frame? For example, if a car is a non-inertial frame, since it moves with acceleration a with respect to the ground, these kinds of accelerated frames, okay, the car with the accelerated frame, that means a person inside the car sees this person standing outside in the ground, then it will be the non-inertial frame. Remember, the person standing outside the car who is in rest is having an inertial frame, and a person inside the car who is seeing the person standing outside the in the ground is in a non-inertial frame. There is a difference between these two frames, because a person inside the car is on movement. He is having a force to move from one direction. Now, the rotating frame is also a non-inertial frame. Okay, since the rotation requires the acceleration. While you are in a merry-go-round in festivals, you can see a lot of merry-go-rounds. Using that merry-go-rounds, you can move in a circular motion from top to bottom. If you are in that merry-go-round, you can see a frame of a person who is standing in the ground. That frame is also non-inertial frame. Newton's second law. Whenever the momentum of the body changes, there must be a force acting on it. And the Newton's law states that the force acting on an object is equal to the rate of change of its momentum. That's why I told you, whenever the momentum of a body changes, there must be a force acting on it. And we know force F is equal to d vector dp vector into dt. Here let's see what is the p. The momentum of the object is defined as p is equal to mv. That means here you can see p is equal to mass into velocity. P is equal to mass into velocity. Here p referred to the momentum. While doing the derivations, we get f vector is equal to d into mv. We are substituting this mv instead of this p. So d mv by dt, we can split it as m into dv by dt. That means the dv by dt is equal to acceleration. Therefore f is equal to mass into acceleration. Force is equal to mass into acceleration. In the SI unit of system, the unit of force is measured in newtons and it is denoted by the symbol N. In most cases, the mass of the object remains constant during the motion. Okay, there is no change in the mass during the action. And let me explain the 1 Newton also. 1 Newton is defined as the force which acts on 1 kg of mass to give an acceleration in 1 meter per second square in the direction of the force. This is called 1 Newton, and this is also an important 2-mark question. See, it is to be noted that Newton's second law is valid only in inertial frames. In non-inertial frames, Newton's second law cannot be used in this form. It requires some modification because the above equations, this equations conveys that the fact that there is an acceleration. While there is an acceleration, the inertial frames cannot be present there. Aristotle was Newton's approach on sliding objects. See, from the beginning, Aristotle told that external force needs to be applied to move an object with constant velocity v. That means the net force is equal to force into external. Here, the balls need an external force to move from one place to another. That means the displacement needs an external force. Like this. There is a one object. The man is using a force to kick the object. He wants to throw it to some certain distances. So he kicked that object with his golf bat. Now Galileo and Newton, really a controversial statement from Galileo and Newton. There is zero net force on the object when it moves with constant velocity v. That means the net force is equal to 0. They told that net force is equal to 0. F external force which is given here. The Galileo teaches about the frictions. Okay, but Aristotle don't worry about that. But this Galileo and Newton cares about the frictional force. In this picture, two persons are pulling and they will have a force from both sides. Okay, this is so the net force applied from here, both the persons are 0. Newton's third law. Newton's third law states that for every action there is an equal and opposite reaction. Okay, in this picture you can see what is the reaction for every the bullets are coming out from the gun. There is an equal and opposite reaction towards the backward side which that person is feeling here. Okay, any one of the force can be called as an action force and the other as the reaction force. Let this be, the one is action and another one is reaction force. Newton's third law is valid in both inertial and non-inertial frames. That you know more about the Newton's third law. Now let's discuss on Newton's laws. Newton's laws are vector laws because it has both direction and the magnitude. While force is equal to mass into acceleration in Newton's second law, in Cartesian coordinates the equation is Fxi cap plus Fyj cap plus Fzk cap is equal to Ma xi cap plus Ma yj cap plus Ma zk cap. We substitute here with mass into acceleration, and by comparing the both sides, the force and the mass into acceleration, the scalar equations are Fx is equal to Max. The acceleration along the x direction depends only on the component of force acting along the x direction, and the second one Fy is equal to May. The acceleration along the y direction depends only on the component of force acting along the y direction, and third one Fz is equal to Maz. The acceleration along the z direction depends only on the component of force acting along the z direction. The acceleration experienced by a body at time t depends upon the force which acts on the body at that instant of time, and it does not depend upon the force which acted on the body before the time t, which is expressed as Ft is equal to Ma into t. That means force with respect to time and mass into acceleration with respect to time, which can be proved using an example. Okay, when a spin bowler or a fast bowler throws the ball to the batsman like this picture, once the ball leaves the hand of the bowler, it experiences only gravitational force and air frictional force. The acceleration of the ball is dependent of how the ball was bowled, that means with a lower or a higher speed. Okay, so let's move to the third. In general, the direction of force may be different from the direction of motion. We know the deceleration, that means which is opposite to the acceleration. Though in some cases the object may move in same direction as the direction of the force, it is not always true, and few examples are given below for you. The first one, force and motion are in same direction. Let's see a picture. Here Newton is sitting here and the apple is on fall. Okay, that picture and the motion which you know very well. When an apple falls towards the earth, the direction of motion, that means the direction of velocity of an apple and the force which it acts oppositely, the gravitational force also, are in same downward direction, and this is called the force and motion in the same direction. The second one, force and motion not in same direction. See, the earth experiences a force of towards the sun, but it actually moves in elliptical orbit. In this case, the direction of the force is different from the direction of motion. If it happens, that means the force and motion are in same direction, then we will sit in sun. Is it possible? No. And the third one, force and motion in opposite direction. If an object is thrown vertically upward, the direction of motion is upward, but the gravitational force is downward. The juggler using the ball, but the direction of the ball is towards the ground. Fourth one, zero net force but there is motion. What are that? When a raindrop gets detached from the cloud, it experiences both downward gravitational force and upward drag force. You can see this umbrella experiences a downward air drag force from the raindrops. As it descends towards the earth, the upward air drag force increases, and after a certain time the upward air drag force cancels the downward gravity. Hence the raindrop comes with zero net force. Therefore the zero acceleration but with non-zero terminal velocity. While the raindrop reaches the umbrella or the ground, it will have zero acceleration and it will have a non-zero terminal velocity. Then the fourth one, if multiple forces, okay, F1, F2, F3 or till let's go to Fn, act on the same body, then the force, total force F net is equivalent to the vectorial sum of the individual forces. Their net forces provides the acceleration. Using the term F vector net is equal to F1 plus F2 plus F3 plus dash 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 Fn vector. Newton's second law for this case is F net is equal to mass into acceleration. In this case, the direction of acceleration is in the direction of the net force. You can see an example here, a bow and arrow. Fifth one, Newton's second law can also be written in the following form. That means, since the acceleration is the second derivative of a position vector of the body, A vector is equal to d square r vector divided by dt square. Here r refers to the displacement. The force on the body is F is equal to m into d square r vector divided by dt square. Sixth one, if no force acts on the body, then Newton's second law, m dv vector by dt is equal to 0. That means mass into acceleration is equal to 0. It implies that the velocity vector v is equal to constant. It is essentially Newton's first law. Newton's second law is cause and effect relation. Force is the cause and relation is the effect. Conveniently, the effect should be written on the left and cause on the right hand side of the equation. So the correct way of writing Newton's second law is ma is equal to f, or dp vector by dt is equal to f vector. Already you know p is equal to momentum. Thank you students. Thank you for your participation. Study well.